Hi everyone, my name is Michael Stewart. I'm from the University of Western Australia and I'm a research fellow at the ARC Training Centre for Transforming Maintenance Through Data Science. My talk today is called Unlocking Knowledge in Maintenance Work Orders with Echidna and Redcoat. So I'm going to start my presentation with an overview and a motivation. I'm then going to demonstrate Echidna, which is a knowledge graph supporting visualization and querying of maintenance work orders. Finally, I'm going to demonstrate Redcoat, which is an annotation tool that supports technical language processing. So maintenance management systems capture a significant amount of structured information, such as functional locations, costs, dates, and downtime events. However, a significant volume of the knowledge held within maintenance management systems is unstructured. It's captured within the short text descriptions, the technical language. This short text often contains indicators of failure modes and end-of-life events, which are directly tied to mean time to failure values. However, despite the fact that it contains such a wealth of information, it's seldom used for routine analysis. So here's an example of some work orders. We've got the start date and functional location description, which are structured fields, and then we've got the short text, which is unstructured. We can see that a lot of the valuable information here is actually within the short text. For example, repair is the activity that's been performed here. Cracked is the failure mode in this case for the hydraulic tank. And likewise for the second one, engine is the item, won't start is a failure mode. It's another way of saying that it's a failure to start on demand. So how do we go about incorporating the unstructured data and the structured data together so that we can use it for decisions, for making decisions about maintenance? Really, the best way that we can do that is to use knowledge graphs. So constructing a knowledge graph that captures the knowledge held within the unstructured text and also the structured information allows for some vital information to become highly accessible, such as how many times have pumps in a certain location been replaced in the last month, or other pumps failing in ways that we didn't expect. So now I'd like to demonstrate Echidna, which is our knowledge graph for maintenance. So here we have Echidna. This graph has been built automatically using machine learning. We've provided it with some training data, and the machine learning model has built this graph automatically. And each of these circles represents a particular type of entity in our data. For example, the greens are items or assets, the reds are observations, and the blues are activities. Now, if we click on an item, we can see the number of times that that item appears alongside another node in the work order. For example, leak up the top there has 3. So that means engines and leaks occur 3 times together in our work order data set, essentially meaning that in our data, there's 3 engines that have had leaks. Now we can also use this hierarchy on the left to sort of drill into our data and to filter. So right now we're looking at all the rotating equipment in our data set. We can also filter down into, for example, pumps, which are a subclass of rotating equipment according to the ISO 15926. Now we can also aggregate these as well. So right now, each of these pumps is represented by a single node, but maybe we want to combine them all together to get an idea of how many times, for example, pumps have had leaks in our data. In this case, 8 times. We can see with the leak there. We've also got the ability to look at the structured fields in our data and to incorporate that into the graph so that it can be queried. So for example, we might want to look at a particular date range. So we could generate the graph based on a date range. We've also got functional location description. So let's say, for example, we're interested in an engine lubrication system, for example. We'll go ahead and click and apply. And now we've got a graph that's been generated just from work orders where the functional location is engine lubrication system. In this case, it's just one work order where there was a leak that required checking. We've also got the ability to filter by work order type, so PMO1s or PMO2s, that will generate the graph based on those. And finally, we've also got the costing. So for example, if we type in 30,000 here, we can generate the graph where the cost was between $30,000 and $50,000. And those costs are simulated in our data set as it's a publicly available data set. Now, one of the most notable features for that graph is that we've also got the option of looking at functional locations as opposed to items from the work orders. So functional locations are of significant value to reliability engineers who have a clear idea of all the functional locations of their plant And functional locations are arranged in a hierarchy. What that means is that we can actually look at various functional locations using the same method we did for the items. So maybe looking at these particular functional locations within 1234.02, or perhaps we want to look at, all of the ones within 1234.02. And of course, these functional locations are also simulated. These aren't real locations, but we have applied this graph to real world data using real functional locations. This is just for demonstration purposes. So let's say, for example, we look at 1234.01. So here's a graph that's been built from that. And we've also incorporated AMPLR data as well, or delay accounting data. So these are downtime events that have occurred at some point in time relating to these particular functional locations. And they also have the sort of effective duration and loss feed on the node as well. And similarly to the item nodes, we can also aggregate functional locations. For example, now we've aggregated every single functional location sort of subclass of 1234.01 into one node. So we can get an idea of how many times, for example, this particular functional location has had a leak. And not just this functional location, but every functional location within it. So now we can see that we've got 31 leaks on this particular functional location. Now, something else we've also got in the graph is the ability to aggregate observations. And this is super important for failure modes and effects analysis. The fact that we've got so many different ways to represent the same failure mode. For example, leak could be written as leaks, leaking, leaked, etc. We've started work on actually aggregating these observations together according to structured failure mode codes. For example, electrical. If we look at all the electrical nodes, we can aggregate them all into the single node. So now we have an idea of how many times, for example, this functional location has had some kind of electrical related issue. So now that I've talked about the graph and have demonstrated the graph, I'd like to talk a little bit about how we build it. So really, as I mentioned before, the graph is automatically created using machine learning. But in order to do that, we rely on high quality labeled data. So essentially the pipeline is as follows. We start with creating some labeled data ourselves. We input that into a deep learning model, which then produces machine labeled data, which then goes through a knowledge graph construction stage in order to build the graph using that machine labeled data. And finally, that provides the decision support. So how do we get that labeled data in the first place? Well, our solution is Redcoat, which is a collaborative annotation tool. And we've been using Redcoat to produce training data to be able to build that graph that I showed you. So I'd like to provide a quick demo of Redcoat. So this is Redcoat's projects list of projects that we've got in Redcoat. If you go ahead and click on one of these projects, this is the sort of annotation dashboard showing some sort of key information such as the average agreement across all of our annotators on this particular project, some of the entity frequencies of the project, the activities of all the annotators. We've also got a commenting system so that we can collaborate on refining our entity hierarchy and assisting others with being able to understand maintenance terminology and so on. Go into the into the annotation interface. This is how it looks. So essentially the task is to label each word or sequence of words with their corresponding entity class. So inverter in this case is an item, not working could be an observation, and so on. So in conclusion, we've presented our work on unlocking knowledge within maintenance work orders via two powerful tools, Echidna and Redcoat. These tools work to create a knowledge graph that provides reliability engineers with the ability to easily access and query their maintenance work orders, providing an unprecedented level of decision support. Thank you very much. I've included my email address there, so please feel free to send me any questions you may have. And feel free to check out the Centre for Transforming Maintenance Through Data Science website and the UWA Natural Language and Technical Language Processing group. I've also included links to demos of the two tools that I've presented today. Thanks very much.